Okay, so uh, recently you might have seen Xiaofeng and Guanqi paper on aerial manipulation, and aerial manipulation is a really cool domain because like you're able to do really cool tasks that you aren't able to do with any other robots, or at least in a really scalable way. Um, for example, like light bulb mounting, light bulb unmounting, valve rotation, pick and place, but not really even limited to these stuff. Um, but as things currently stand, like uh, these kind of like if you have an imitation learning policy for let's say light bulb mounting, you're kind of stuck in the lab settings. You can't really move from. You can't really just deploy these policies, these autonomous policies, anywhere in the world. And the real motivation for my project is how do we get these policies in the real world? You can imagine like really complicated tasks, like I think on the bottom right, you see a house, and currently we have drones that are able to, like, for example, go waypoint to waypoint every week or something, like from a home base station where it just like goes around the house, takes some pictures, and then you get to see them on your like phone. This is from Skydio. Um, basically it's for inspection. But you can imagine a different future where like you don't only do some inspection or take some images, but you see, okay, you take that image, you see, okay, my light bulb doesn't work. So I can autonomously roll out that policy to like unmount or remount the light bulb. So there's a really big um, use case for aerial manipulation in the real world. Um, but as things stand, our current solutions are perhaps large scale data collection. So how do we do these kind of data collection? You typically have like a controller, Xbox controller or something, where you see the image observations from the drone, and you um, you control the drone in different environments. And, and this is like a great solution if you look like this guy, um, um, where you have a lot of money, you can deploy your drone everywhere in the world. You have like hundreds of people collecting data in like a lot of diverse environments, but this can get really expensive, and I don't really believe that this is the solution at this time, at least. Um, we have another different solution from, okay, many of these different like leading manipulation labs. They've kind of um, they're all trying to converge to, or we've kind of seen them all kind of converge to a similar type of manipulation interface, where they have a camera that's situated on the gripper, and like basically the camera sees the gripper, and you kind of uh, operate in an egocentric environment. Um, and in this way, they can also leverage cross-embodied latent representation. So this is a work from this is a work RDT, which uses 46 data sets of consisting of millions of episodes of multiple different robots, and it's um, they're able to build a implicit latent representation by pre-training on a huge amount of data from different robots, but um, you still aren't able to make that jump to a new robot without a fine-tuning phase. Um, in this data set, they create another data set of a number of episodes on a new target arm, and without that fine-tuning step, you can't really even. Your performance is still 0% because you're not aware of your own embodiment without extra data. Um, recently, we've seen some more progress on cross-embodied explicit representations. Excuse me. Um, so on the top left, you can see a universal manipulation interface. On the bottom left, you can see robot utility models. So the observation space for like your data collections and your robot setup are completely the same. So imagine you were even collecting on one type of robot and you want to transfer it to another type of robot. Well, at least in your observation space and your action space, things are completely aligned. And this is kind of useful because, oh wow, that's loud. I don't know if you can hear that. I'm just gonna pause that. Yeah, um, you can you can end up collecting data really easily because you don't even need a robot um, to do your data collection. You can just pick up the gripper and then start collecting data anywhere under 2 minutes. And then because of the nature of the data, that okay, you can collect it anywhere. You can also deploy the policies practically anywhere. Um, but there's like this unsaid, unspoken rule that in a paradigm like that, your robot cannot be under actuated compared to your data source. And what do I mean by that? So this is one example where the universal manipulation interface, they show um, a human collecting here where he's collecting data of a throwing task where he's putting it into he's trying to put the objects into a box by throwing it. But imagine your robot cannot effectively match those actions. Um, I mean, yes, this policy does have an 85% success rate, but is the 15% failure rate because one, the policy is not good enough, or because the robot cannot fulfill the actions? And there's no real um, way to attribute this correctly at this time. So, I mean, you could say, harsh, you could measure the amount of, or like if your policy outputs certain actions, you can measure how well your robot is following this. Following these actions, you can compute some kind of loss and say, okay, maybe my robot could not um, fulfill the actions maybe 15% of the times, but it's still interesting that it could do it 85% of the times, meaning that there are modes in your distribution that the robot can fulfill, whereas there are some other modes that maybe you can't fulfill. And this problem gets like exacerbated when you don't have guarantees on the actuation of the robot. Like all of these different systems, like they all have grippers on different types of robots, like quadruped, a drone, underwater there's an underwater manipulator. There's also humanoid. So you don't really have um, all of these embodiments have some severe constraints that limit their motion, even though they're in a 6 degrees of freedom end effector space. Um, for example, um, I I mean, I think you guys get the point. And it's quite difficult to attribute. Okay, and how are you supposed to even measure in that way the effectiveness of UMI? Like how much of the failure is attributed to embodiment mismatch? And in real life, I'm not aware of any robot that can perfectly follow any action sequence that maybe a human can generate like very randomly or like even purposefully. Um, but that's in real life. There are definitely solutions for us to look in simulation, for example. So here's an example of me collecting some data, like UMI style data in simulation where I have a gripper and I'm moving or like I'm taking a can out of a cabinet and placing it on the top of a cabinet. And in my data collection, the main randomization came from randomizing the location of the can and starting location of the gripper. And you can kind of test policies in that way by executing the same UMI device onto in the simulation itself, and you can see that. Well, in this case, at least, if you had a perfect robot that could perfectly match the actions that you um, or perfectly match the action outputs from the diffusion policy that you're training, you can achieve 100% success. And so it's interesting when you then transfer that exact policy to a drone environment, and you can kind of see that it does not perform at the same level. Like there's at least a 20% embodiment mismatch. Um, in this case, there's actually no disturbances or noise that the drone is experiencing, unlike what real drones experience. And you can see some of the failure cases that the drone ends up experiencing. Um, so here, the drone kind of gets stuck on the handle, and like some of the failures come from there. Um, and I mean, this is a successful case opening the door, but it's not able to perfectly, um, grab the can and kind of misses. And these are not failure cases or like seen at all in um, the UMI embodiment. So our actions aren't being perfectly followed in this case. And but it's also important to note that all of these errors come from either constraints in your controller or robot, and also from predictable momentums. But we also have a different case where errors can come from unpredictable factors. So this is another task where I collected some UMI data and I'm transferring it to a robot. And so the task is to insert a 1 centimeter peg into a 2 centimeter hole where I'm randomizing the location of the peg. And this time I added noise levels that were similar to real life, which kind of translate to around 3 centimeters on average of end effector error. You can see here, like the drone kind of really struggles. It's a really hard task to even do in teleoperation. Um, I think even I have a like 50% failure rate if I was to do it um, while teleoperating the drone itself. And you can kind of see like, okay, while on the UMI embodiment, we had 100% success rate. On the drone environment, without noise, we also have 100% success rate. It's a quite simple task where I'm going towards the peg, or going towards the hole with the peg, aligning myself, and then inserting the peg into the hole. But when you add noise or like some unpredictable factors, your policy kind of falls apart. Um, so you can imagine what's happening. So this is the cabinet task where we're trying to put the can um, on top of the cabinet, and you imagine if your reference trajectory was going up to the up on top of the cabinet and trying to place the can. And imagine you had some noise at that instant, making the drone's momentum high in the X direction, so like towards the right side, or you had some constraints that prevent the drone from elevating that fast. The diffusion policy has no awareness of those factors, and it'll still produce the same reference trajectory because that's the most probable um, trajectory in the pre-trained distribution that we have. And so what would happen is when you execute that trajectory, you end up hitting the cabinet because of those either constraint or the noise that you had. But the fact is that in my data collection, and like for example, I had 100 episodes of me doing the opening the cabinet, placing the can on the top of the cabinet. There are definitely other modes of data that are more feasible for the robot embodiment or this exact embodiment to do, but we're just hoping for random luck that we maybe get reference trajectory 2 rather than reference trajectory 1. And I want to discuss about, okay, how can we get that reference trajectory 2 instead of the reference trajectory 1? How can we get something that's more in line with our controller rather rather than something that the diffusion policy outputs randomly? So I, I think that was a good time to get into how or what kind of controller that the drone uses. For the drone, we've been using a MPC, model predictive control, um, which predicts the future behavior um, of the robot over the horizon, over a certain horizon, and then optimizes control inputs over that window. So like if you give it some reference trajectory, it will try to optimize the control inputs over that reference trajectory. So the state is built out of like the end effector position and the base velocity, the joint angles, and your input spaces, the control range of the drone, and the commanded joint angles. So if we build our error function or like our cost function is built out of like these four main terms. The first term is the tracking term, which is the main objective term. This is basically telling your end effector to be in a certain location. And we have like some other regularization terms to, for example, keep the velocity in checks, because like you can't have the drone with some random, I don't know, super high velocity to do all these to like follow the end effector. You can't. It's very detrimental to have the drone's arm really far extended out, because that makes the drone's like base position kind of, or the drone's base or center of mass like messed up. It like kind of makes the drone's base tilt in front, which is kind of unstable. We also don't want, um, very high inputs, stuff like that. But the main term that we are focused on is the tracking error. So the tracking error kind of tells us how, or imagine you have this trajectory from the diffusion policy, where like x is your trajectory and x0 to xn is your shooting nodes. So like each of these nodes has the reference position and the quaternion for every single action in the future. For like imagine like 8 actions into the future. You can pass that into the NPC and then calculate a tracking cost. And you know that if this tracking cost is high, that node is difficult to track in that um, in that trajectory that you passed into it. And you can kind of see on the top left, I drew two trajectories where one is like really all over the place, and it may be difficult, and the NPC might return, okay, this is point 3, this is quite difficult for me to track. But a straight trajectory that is relatively more simple, it says, okay, hey, this is quite easy for me to track. You don't need to worry about me not being able to follow this trajectory. And we can simply just take in Kasadi, you can take the gradients of the tracking cost with respect to the reference trajectory. So each shooting node, you take a derivative of the tracking cost with respect to the reference trajectory, and this kind of tells you how should you nudge the reference trajectory to make it more easy to track that trajectory. And you can end up using it in a system like this, where here you can. So this is the algorithm I'm using to guide the diffusion policy, where xt is the noise, or xt is the noisy trajectory at the start, and you kind of iteratively do the denoising step, but in between you also add a scaled MPC guidance. So that's the like the J term that you can see. I don't know why I can't use my mouse. It's third line, where you're just adding the MPC guidance as well as as well as doing the denoising right after. So line 3 is the only thing that we've added here. So you can imagine you have some observation from your environment, you pass that into your diffusion policy generates some kind of trajectory. It gets sent to the MPC. The MPC like tries to verify it, sees, okay, this is difficult for me to track, and passes some gradients back to the diffusion policy. So this happens iteratively until your trajectory is completely denoised, and then you can send it to the MPC controller or to the drone to be able to execute it. So you can imagine in this case, you're initially you would sample reference trajectory 1 because that was the most probable one in your distribution. But if you add the MPC gradients, then your landscape kind of shifts. Your probabilities kind of differ, and you go closer to a probability map that your embodiment is more likely to be able to solve. And you can kind of see how like that ends up. So I mean, yeah, disclaimer that everything is still in simulation. Um, hopefully, like hopefully next week or so, I should be doing some real world tests. But yeah, that's TBA, or TBD. So on the left side, you see the diffusion policy plus the drone, and then diffusion policy plus drone plus noise. So, I mean, we have a success rate of around like 65%. But you can really like see the benefits of guiding the diffusion policy with the MPC, where so like the first one, without noise, you completely are able to bridge that predictable momentum and constraints, but still noise, we still suffer some issues here. Um, because of how unpredictable noise can be and the nature of diffusion policy, because we're generating like let's say 0.7 seconds worth of actions at the instantaneous time step. So like you don't really know what's happening at 0.3 seconds. You can't really like incorporate the MPCs, um, new gradients at that point, because once the diffusion policy generates some actions, that's what you have to execute. Um, So this is some results for the peg and hold task, where initially we had 100% accuracy for like there were no limitation on the at least the constraints or the predictable momentums, but the noise is what due to the errors. And here our policy is able to fare much better because like at least in the instantaneous time steps we're able to tell, okay, um, what is my momentum and how should I uh, account for that when making my actions. And even for those that had 100% success rate, like you can see the diffusion policy plus drone, the MPC carried plus drone, so no noise. Um, our policy is able to completely match the diffusion policy plus like the UMI variant in terms of the average time to success, because we're no longer doing actions that are um, not aligned with the embodiment that we're in. Okay, so I mean that sums up my work for the last 2 months. And yeah, I